Velocity is described by the function v sub x equals kt squared meters per second, where k is a constant and t is in seconds. The particle's position at t sub 0 equals 0 is s is x sub 0 equals negative 9.0 meters. At t sub 1 equals 3.0 seconds, the particle is at x sub 1 equals 9.0 meters. To determine the value of the constant k, be sure to include the proper units. So the first thing we want to do here is just write out our knowns in order to develop a strategy to solve for that constant k. So we were given that velocity function, kt squared, meters per second. We were also given a bunch of numbers, which show a relationship between time and displacement, or rather, position. Which means that these these numbers can just be put in coordinate pair form, and those coordinate pairs are going to directly correlate with a position versus time graph. So we have a situation where we have a velocity equation, but coordinates from a position versus time function. So the thing that will help us here is just that we know from the kinematics equation that velocity is change x over change time, which you manipulate a bunch, and it turns out that you can just integrate the velocity, and that will get you the position versus time equation. And I kind of modeled that on the left, or rather the right, where I drew what that velocity function is kind of going to look like. We don't know the altitude because the altitude is what k indicates. But we can kind of just use this to wrap our head around it. That shaded part, the area under the curve is the integral. So that's why I showed that shaded part, because that integral is going to be that position versus time function that we're going to find in our next step. Okay, so this is that next step in which we integrated the velocity equation. I just want to reiterate the reason why we're doing that is because our points are points from a position versus time graph, and we want to be able to plug those in to our equation in order to do some algebra and solve for k. So yeah, I went ahead and integrated it. It comes out as x of t equals k, t cubed over 3 plus c. Can't forget that c. The c is incredibly important. You're going to get the wrong answer if you don't include c. You might be wondering, be a little bit confused about how to integrate with that k. Since we know k is a constant, just like 1, 2, 3, all those numbers are constant, we can just yank that out of the integral and have it be multiplied in at the end. So yeah, now we have our position versus time equation. So the first thing we want to do is just go ahead and solve for c. And we were given that 0, negative 9.0 coordinate pair, which will make this pretty easy, because once you plug in that 0 for t, it makes that whole part of the equation 0. The k t cubed over 3, it makes it all 0. And so it just ends up coming out as c equals negative 9.0 meters. So if you plug that back into the original equation, if you plug c back into the original equation, you get x of t equals kt cubed over 3 minus 9.0. And now we can use that second coordinate to do some algebra, solve for k. Okay, I did some algebra, simplified it a bit, got 9k equals 18. 18 divided by 9 is 2, so k equals 2. Feels like we're done, but we're not. We still have to figure out the proper units. So you can kind of use logic or some pretty simple algebra to figure out these units, since we now know that Vx equals 2t squared meters per second. We know that the t squared is going to have is going to correlate with second squared. So we just have to figure out what we need to multiply second squared by in order to equal meters per second. And that comes out as meters per second cubed. So those are going to have to be the units of 2 in order to make that equation work out. So our final answer is just 2 meters per second cubed. And now that we know that, we can do a little bit more with this whole situation if we want to. We could differentiate the velocity function and get acceleration. We can plug in a bunch of points and get a more accurate representation of the velocity curve that I showed earlier. So yeah, we can do a lot more. Thanks for watching.